In the last class, we were discussing about the prime producing chemicals, and now considering these kind of things, so we are considering two variable things, and which are the forms. So the most basic case, that is x squared plus bxy plus cy squared, and suppose as in the case of the Jones-Sandberg polynomial, J is transitory polynomial, we saw that all the positive values taken by the polynomial are primes. Now, if this is so for such a thing, such a form where these are integer coefficients, we are going to face a trouble. I mean, this is not possible. So the question is, there doesn't exist any polynomial and binary polynomial integer coefficients or inequality form. With integer coefficients such that, suppose there is a form such that all the positive values attained by or taken by the for all intermediate inputs are the positive. So what we asked is that if of n intersection n equal to the set of primes, this is an impossible condition if this is a particle form. Why? Yes,
sir, like for a single variable case, that is not a subset of P is infinite.
So sure. This this is that this is not empty.
This is not. So it has at least one positive image.
Sure. Yeah. Let me summarize. This is an impossible condition. There is such a thing that it is non-empty, and whatever value it takes is a prime, and whatever positive value it takes is a prime. It's not possible.
We didn't prove this.
No, we didn't prove this, but actually it is a simple to see. Because suppose it takes a positive prime value for some x0, y0. So suppose f of x0, y0 is a prime. Okay. Some t, because we assume that it is not empty, we can say that there exists some prime. Now consider this. So this is just 4p. Of course, it's positive, and then it should be a prime by the assumption, which is not. Because it's a quadratic form. So you can, if it is taking prime value for some x0, x2, you can just take it to x0, x0, x0. So again, it is a question for you to think about. So, does there exist conic over section? Does there exist such a polynomial phi candidate polynomial with x, y, that is
The general quadrant.
right, x squared plus bxy plus cy squared plus ex plus fy plus g such
that?
That if in N, that is you are taking natural inputs in intersection N, which is giving you all lines. So I don't know the answer to that, but this most likely there should not, because well, if you recall the construction from the Jones set wire lines, how did we proceed? This was simple algorithm when so let's recall what is the definition of a Daffodil set. So we call some set is a subset of N some R is narrow and done if there exists a polynomial if such that f of x tilde y tilde is equal to 0. Well, at first we must define what is the what this polynomial f is. So I don't know why do we say that f exists. So let's work this out and write it down. Clearly, polynomial if in some z x1 xr and y1 y is say such that if of we call this set of variables x tilde, call this set of variables y tilde, and if of x tilde y tilde is 0 if and only if x tilde is inside the set S. So it's a concept similar to the indicator function, but this is taking the value 0, and x tilde is so for every x tilde in S there is some solution of this in terms of y, and if there is such a y for this for what this happens, then this x tilde must be double.
Small s is fixed or
No, small s may depend on this R or depend on set S. So if you look into their construction or the construction of IISER, they actually constructed such polynomial for Daffodil sets. Well, I think examples are rather easy to figure out. For example, if you take the set of odd numbers or possible integers, then you can actually have, like, if you write it to if each x you can write it as 2 is 1 or integer inputs y, and then you can easily construct such polynomials. For easy sets, it's rather easy to construct such polynomials. Whereas now let's take the main idea from this or the paper from Matthias Crick. What did they do? They were thinking of that. Suppose there is such a polynomial, then they were just looking at things like this. So if we call this polynomial, well, if is fine. Suppose now we are considering P as our this set S. So what is the theorem of Matthias Crick? That is, every competition in your set is definite. You can list the elements of S by an algorithm. You know how to compute them. Then there is such a definite description of this. Okay? So then there is such a polynomial which will satisfy this property. So that in particular means that if you choose if x y tilde is such a polynomial is this polynomial here, and then consider this polynomial g x y tilde defined in this manner 1 minus g x y tilde.
Oh, okay.
Or just square root squared. So what is happening? Now note that this is an integer polynomial. Whenever it is taking a non-zero value, this will, well, unless it's, even if it is 1, it is 0, or it is negative. Unless this is itself 0. In that case, x will be inside the set s.
Will it only be a inside?
Ah, right, thank you. Yeah, I mean, sorry. So gxy, if you define in this manner, I mean, if you have a diagram description of the set in this way, you can always write down something, and then this all the positive values will be those ones for which this is 0. So that's how they computed. I mean, given the diagram description, they could find such polynomial. Okay. Now note that here we are using a square, okay, and here we are using x. So that, I mean, given their construction, such a thing is not likely to exist. I mean, at least from the way they constructed the polynomials.
So the proof of this also goes the same like polynomial. If we put it, suppose there is a line, like the x naught, y naught, we can take p plus x naught and p plus y naught.
P plus x naught and p plus.
Then that will be divisible by p.
Okay, so suppose.
Suppose x naught y naught, if of x naught y naught is prime.
Yes. If of
X naught
y naught
prime.
is a prime.
So we have to find f of x plus p and y plus p.
If of x,
I mean x naught plus p and y naught plus p.
okay. If of x naught plus p, y naught plus p.
So that will be something f of x naught y naught plus some p into some number.
Right.
So that is divisible by p.
Sure, but how do you ensure that this is not negative?
So
How do you ensure that this is not negative? And if you still need that this is in the set of natural numbers. So there lies the difficulty, because for every y, there will be only finitely many x for which this takes positive values, and for each x, there should be only finitely many y for which this takes a positive value. So this needs to be, this x0 plus p, y0 plus p should be in such a range that is this value is positive. If that is the case, then your argument is fine. How to ensure that? That's a question.
like you can put x naught plus some k to p, like then taking k large.
That won't work either, because I mean, you see, because of this condition, actually, this both these coefficients a and c will turn out to be negative. Okay. So for both large, it's not guaranteed that this is going to have some positive. So yeah, this actually needs more thought. Which part should I hear? This one? And since I talked about most criteria once, but it was not in the not recorded, let's just recall it for a while. Let P be a prime and express it in some ways. Okay? This B expansion criteria says that consider this polynomial fx, which is an is for n plus whatever plus a1x plus a0 in zx, then this is irreducible. So there's a beautiful exploratory article by Ramurthy on this. You can go and check it. It was American Mathematical Monthly in 2003 or 2002, I forgot. Around that time. So the next thing that we are going to talk about are lower bounds of pi x. We once got it from Nairs argument, and also we will get it from Chebyshev argument. And
last day we did.
For Chebyshev, we did half of the proof. We left the rest for discuss. So at first, let's. We said that before we do Chebyshev, we will complete Nairs proof, and then we move on to Chebyshev. So did you try to figure out this integral formula? That is, on the left hand side you have an integral, on the right hand side you have a binding integral. Alright, let's derive it first. And we'll use some statistical tools to derive it. Nevertheless, it's an incomplete beta integral, and so if you look at the relation between beta integrals and the gamma function, it's rather easy to obtain. Minus 1 minus b power a minus a b cubed, and that was equal to 1 by 2 times this. So what you can do is that you can expand this binomial expansion and then multiply with this one and do diagonalized integration, and you will log on this one. That's a way of directly proceeding. But you can also derive a more general version of this from statistics. Let's do it. So suppose here's population. With this one of the same B independent random variables with common CDF if then the CDF of the jth order statistic is given by if x is summation r running from j to n choose r if x whole power r and 1 minus if x whole power 1 minus. Okay. So if jth order statistic seems, I mean, if you're not familiar with this term jth order state space, let's recall what we mean by jth order state space. So these are the, I mean, some of the vectors, right? And you can write down the values that they take. Suppose they are taking values in some rather easy distribution, say binomial or even Barnum distribution. I mean, they're just taking values between 0 and 1. So if you write their values in a non-decreasing way, that is, the values taken by x1 is to xn, they will be some set of 0, 0, 0, 0, and then 1, 1, etc. So now, what we do, we arrange the values taken by them in a non-decreasing way, like this. And then we say that this one is the minimum of the values taken by them. So minimum of the, then we try the minimum. That is, we try the value that x1 has taken. There could still be the same value there. So if we try by 0, there could be another 0 there. We don't care. We just define this to be the second minimum of x1 over xn. So that is, if you organize them in this manner, write down them in an ordered fashion, then it is just the second value. And similarly, xj is the jth minimum. Xn is the nth minimum, that is the maximum of the values. Okay. So that is how you define order space. x1, x2, xn are random variables, independent random variables. These are also random variables, and of course not independent, because the value of x2 will depend on x2. The value of x2 is always greater than the value of x1, greater than or equal to the value of x1, and so on. So they are not dependent, but they have a relation like x1 is equal to x2. For example, if all of them take the value 1, then x1 is taking the value 1 as well as xn is also taking the value 1. And same for 0. Now suppose we want to get this one. What is the definition of the CDF of random variable? What is this?
Yeah.
The probability is n is an equal to x. Right?
Definitely all lower.
All the lower ones are less than equal to x, and possibly some upper ones too. So all we know is that at least j of the random variables are taking values less than equal to x. So that means you are summing over j to n the j of the random variables are random variables and assuming values which are less than or equal to x. So here it was at least j, and then you are summing over from j to n, so then you are actually summing over exactly j. So it was random variables x1 xn is j. Now we are summing over for all the r's starting from j to n, and we are saying that it's exactly. This one, now exactly j, that means that, oh sorry, exactly r, because we are varying r. Now we have to, and we can choose this r random variables and we can choose our place, right, from the given set of random variables. So this is the sum r varying from j to n choose r, and then it is p of x, well, for each of the choice of this random variable, say x n1 under x n r, the sequence of random variables that you are choosing from x1 to xn, each of them are having this x n I is equal to r, and you know what it is. The CDF, the common CDF is given to you, right? So it is. So this is exactly the value of the CDF. And how many times and how many of these there are, and they're independent. So you can take the product of them. So you have this for R, and let's write it down here. Fix for R. That is the probability of the R random variables taking values. Exactly R random variables taking values which are less than equal to x. Not exactly R yet, because this is the values of R random variables which are less than equal to x. But exactly means that the rest of the random variables are taking values larger than that. What is the probability of that?
1 minus
Perfect. So that is 1 minus fx, and then how many?
n minus 1.
So that's what we wrote down here. It's just coming from how we define the order test. It's just from the definition. So next, already, if yeah,
Uniform
or letter, yeah, sure.
for the
Yes.
that integer.
Right. Well, actually, you can also, what you can do is that you can just think of this. I mean, you can replace f of x by some variable a, and f of t when t is varying from over the range, like minus infinity to x, to be your variable u. If you think of the integral that you have written down. Or of course you can take it to be from random variable in the range 0 to 1.
Yeah.
That will also work.
That has to be the variable that you are substituting as a function that has to be modeled.
Right. And it is because fx is non-decreasing, right?
Yeah.
So yeah, again. So what is the order? That is if the CDF is differentiable, then PDF of xj is given by j, choose j, sorry, j times ncj, and what you have here, fx will power j minus 1, 1 minus fx whole power n minus j times f dash x. it is like the common term here, but since we are differentiating this delta and delta dashes here, it is j minus 1. We derive this. So we will derive it by directly differentiating that city. So again, can I clear this part up?
There will be a cancellation of.
Exactly, it will be like it else to be sum. And that is so that expression summation we can write actually the summation outside. So summation r d from j to n into r dx fx over r 1 minus fx over n minus r. That is giving you what? R from j to n into r. Here you are having r fx over r minus 1, 1 minus fx whole power n minus r minus now n minus r comes out. Here we have fx whole power r and 1 minus fx whole power n minus r minus 1 minus 1 visible because of this line n minus r minus 1 and this times f dash x, right? So now we multiply this inside. So that gives you some of r into n. Here you have r times n choose r. Inside you have fx with power r minus 1, 1 minus fx with power n minus r, and what we are having here n minus r times n choose r. Okay. So let's do the multiplication somewhere and write it in a different form. We have it n minus r times n choose r, okay? And that is n minus r times n factorial by factorial n minus r factorial. Right? So you can write it as n factorial by r factorial times n minus r minus 1 factorial. So if you multiply here with an r plus 1, this is just r plus 1 times n choose r plus 1. Because you would like to write it in such form.
From second to third line.
From second to third line.
Yeah. What did you do?
I didn't do anything, I just took this inside and multiplied with r. And now we are multiplying this with n minus r, and instead of writing n minus r times n choose r, we will write r plus 1 times n choose r. Minus r plus 1 times n choose r plus 1. Fx will be r times f prime. Now you can see that there will be lots of cancellation. So for the first term, it is j times ncj, exactly what we were looking for. This is the first term. That means the rest of the terms are going to cancel, right? So let's check. It's going to be j plus 1. Right? Now j plus 1 is already appearing there. If you put r equal to j here, that means here you are getting j plus 1 times n choose j plus 1, and here this is fx whole power j plus 1, and this one will be the same thing, j plus 1, if you put it there will be cancellation, so minus j. So here the first term, second term will get cancelled, right? And so on. So there will be several cancellations, and at the end you will just have this one j ncj fx whole power j minus 1 minus fx whole power n minus j times u dash x. Well, we are saying that the second term of the first term is getting cancelled with the of the second first term of the second term, second term of the sum, and so on. So that means that clears up everything except the last term. What happens to the last term? What will be the last term? It will be n choose n plus 1. What is n choose n plus 1? 0.
So that was like when you took the derivative, it was a constant function, so it already it was in the last.
Exactly. So we have this one as one PDF, and this is one of our CDF. Sorry, this is our CDF. Sorry. So this one is our this is one PDF, and this is a CDF of the JG, for instance. So what's the relation between them?
Integral of
Yeah.
integral of this thing over entire.
Exactly. Yeah. We give you the expression, this expression, what we have written down here.
Minus to x.
Yeah, right. So we are getting this. Integral of this expression. J is given to it. J is fixed. And you are taking this J here. And you are integrating this function of minus infinity to x. If t or j minus 1 minus f t whole power minus j f prime. Well, you can write that as dft. Because the range will be here, so you take dt. That is giving you this one. That is giving you the sum r running from j to m. N choose r fx whole power r 1 minus fx whole power n minus. Yeah, so now you can do various things. As you said, you can take the uniform distribution from 0 to 1. That means for the rest, from 0 to 1, you are defining it to take the value 0. If x from 0 to before it is 0, it is just 0, and from 0 to 1,
0 to 1 it is equal.
yeah.
So that we
Yeah, so you can actually
Oh, sorry.
Specialize the distribution in this manner. So you can do several things. One is that you can choose ft such that it is 0 if t less than equal to 0, t if 1 less than t less than equal to 1, and 1 otherwise. So if you do this, what will happen? Just let me know. So which result is doing this? So if you can do this one, put and substitute. U as ft and a as fx. The integral was over u, right? So do the substitution, and this is not for this one. It's a general thing. So if is an arbitrary CDF, you can assume that this is differentiable because we are writing the test here. Just substitute u for this and u for this. See what happens.
So why is this a valid substitution?
What?
Why is this a valid substitution?
Why not? We're just changing the column differently.
But on the left side, when you substitute ft by u, the left side after you substitute ft by u,
Yes.
that is fine. Then the entire thing,
this just becomes dft, that is du.
du.
The range changes, of course. What is the lower range then? It is a value of the CGF at minus infinity.
So minus infinity, minus infinity.
No, it's CGF. What is the value of the CGF?
Oh, 0.
0.
Oh.
And this is fx. This is a.
That would be easier. This one would be easier.
Yes. So can you tell me what you get then? Yeah, the diameters that you get. Even with that second thing.
Second thing, 0 to 1.
Okay.
No, 0 to a.
0 to 2. 0 to a.
U to the j minus 1.
U to the power a minus 1.
1 minus u to the j minus 2. Du
Yes.
equals times that.
Oh, times. That means here you have
J times.
right hand side we are having
Sum of r equals j to n, a to the power n times n to the a to the power n.
a to the power m, a to the power r, right?
A to the power
This r.
r into 1 minus a to the power n.
Into the first have to choose r here, and then the power r minus a
To the n minus and then this becomes binary
right
from j to n.
from j to m.
J to n.
J to m. So this is the more general form that I was talking about. Now if you specialize a to 1, what you get in on the right hand side, what you have?
Like except for r equals n, the rest of the terms will go away.
Exactly. And r equal to n, you are just having 1.
Yes.
So for A is also equal to 1, so you are just having 1. That means. So for A equal to 1, that means here this integral will be, and this thing will be just 1 by 1 divided by. So for example, if you quotient with this term on both sides, you are having this integral here and there 1 by j times n inclusive. So now observe that this this identity could be very nicely used in obtaining a lower bound for IX. So we are going to see that in a moment.
Will it produce better count than Chebyshev?
Well, it's compatible because we are having something like x by log x times some constant. So here's the one. 19 into 2. Well, much later than Chebyshev's proof or proof of the prime number theorem, but nevertheless it's a beautiful argument. So let's see what this. The statement is that phi x is larger than equal to x by log x is 2 for all x larger than or equal to 4. Let's prove it for natural numbers and at first observe these things. What is pi 4?
Pi 4 is 2.
Pi 4 is 2. There are 2 primes. And what is the value of this at 4?
1, 2, so 2.
2 as well. Okay. So pi 4 equal to 2, and that means the case x equal to 4 is done. Also note that 5 by, so this is just combination, 5 by log 5 as 2, 6 by this, 6 by yeah, and also you can actually check that the values and show that this is less than 3, which is equal to pi, what is pi 5? Pi 5 is 3. And that is equal to pi 6. So for 4, 5, 6, we've done. Now, you may assume now that A is larger than equal to 7. Nat's original argument was also for just natural numbers. So let's prove this for natural numbers. That this x is a natural number, and if the notation seems complex, we can also write it in instead. we are going to use this formula, this identity. This is from 0 to 1 u power n minus 1 or minus u to the power n minus j du, and that is giving you 1 by d times n. What we are going to do, we are going to break this primary expansion, multiply this, and integrate downwards. So that implies you are integrating this from 0 to 1. Here you are having the power minus 1, inside you are having the sum minus 1 whole to the power r, say, and you got r as 2. Minus j choose r minus u whole power r. The sum is right from 0 to r equal to 0 to minus j du, and and that is the integral from 0 to 1. If you multiply this now, what happens? Summation r from 0 to n minus j is r minus 1 to the power r u power
j plus r.
wait a minute. This is right. R plus j minus 1, and here you have everything. So if you now integrate this termwise, that means you will have here r plus 1 by r plus j from these ones, and we are integrating from 0 to 1. So let's write it down here. That gives you this summation r running from 0 to a minus j 1 by r plus j times a minus j choose r. So not 1 by r plus j, but there is this minus 1 for r here. This is equal to 1 by a times into z. Okay. So now define Ln to be the LCM of all these numbers 1, 2, 2n. If you multiply the left hand side with Ln, what happens? Well, how far, what are the variables and what is the highest, sorry, what are the values of the denominators, how far the denominators can go? N. Right? So if you multiply the left hand side with Ln, that means that will clear up all the denominators, right? So we have an integer on the left hand side. That means we are going to also have a integer on the right hand side. Multiply this star by Ln, you have integers on both sides. since it is the LCM of 1 to n, you also know that ln divides ln plus 1. So this one also divides ln plus 1. And what this also implies, if you take these two, I mean, if you consider ln plus 1 instead, replace n by n plus 1, that will give you j times n plus 1 choose j divides ln plus 1. Right? Now note one thing. Let's write this down. This is j times plus 1 factorial by j factorial a plus, so n minus a plus 1. Right? So we can cancel j out and get what instead? And take n plus 1 outside. Upstairs you have n factorial. Below you have j plus 1 factorial, and then here you are having what? Wait a minute. N minus, you are having n minus, if it is n choose j plus 1, it will be j minus 1, yeah, oh, thank you. Yeah, then it's n plus 1 times n choose j minus 1. So this is the same as having n plus 1 times n choose j minus 1 dividing ln plus 1. Okay. So this divides ln plus 1, and this also divides, since it divides ln, it also divides ln plus 1. Okay. Now, if you choose j such that j and n plus 1 are relatively prime, then what can you conclude from there? We are having two divisors of ln plus 1. One of them is having j, and multiplied by j, another one is a multiple of n plus 1. And if j and n plus 1 are co-prime, if you choose j so that j and n plus 1, the residual of this is 1, then from this correlation, we get that this is plus 1 because of this.
Sir,
Yeah.
why do you need this ln divides ln plus 1? If the above identity holds for n,
Yes.
because j is fixed, we can just take n plus 1 instead.
Yeah, we are taking n plus 1 here.
No, but do you need that?
Yeah, because now we have to write n plus 1 times j times this. Or, I mean, what I want to say is that if n plus 1 and j are co-prime, then we can actually bring in the n plus 1 factor here.
Plus 1. Yes, that can be done. But that like will you work with ln or ln plus 1?
Which one?
In the next line when you
Well, ln plus 1 actually. Because we are considering everything in terms of ln plus 1. Okay. So that will imply that n plus 1 times j times ncj. This will divide n plus 1. So now that if there is that implies a particular, well, again we have that ln plus 1, the same thing from there, ln plus 1 is less than equal to ln plus 2 because it divides this, and so we have ln plus 2 greater than or equal to ln plus 1, and now suppose, well, at first let's make a choice for n so that this makes sense. So let n greater than or equal to 8 be an even number. Now let n greater than or equal to 8 be an even number, and that means you can choose j to be n by 2. Can you get it? So in this one, if you can choose j to be n by 2, that will imply that n plus 2 greater than n plus 1 greater than or equal to n plus 1 times n by 2. N choose n by 2, you assume that n is an even number larger than or equal to 8, and this one, well, note that n choose n by 2 is the largest binary option in expansion of 1 plus 1 power n, right? And n plus, there are how many terms in that binary expansion? N plus 1 terms. So you can write this, that this is larger than or equal to n by 2 times 2 power n. So this becomes n, well, we assume that n is larger than or equal to 8. So this should be larger than or equal to 2 power n plus 2. Right? This is larger than or equal to 2 power n plus 2. And of course that is 1. So now we are having that ln plus 1 is larger than n plus 1, ln plus 2 is larger than 2 power n plus 2, so on. So we observe two more things. We assume that n is larger than or equal to 8, and here so two things to note is that in L7, that is the LCM of all the numbers up to 7 is 220, which is less than, no, not less than, sorry, which is greater than or 7 or 128, and 8 is 840, which is larger than equal to 8, that is 256. So, in particular, then this one along with that what we obtained here implies that this along with this one is falling double stability. So double star implies along with the other one that Ln is larger than or equal to 2 power n for all n larger than or equal to 7. Okay?
Like, if we take that Chebyshev second function,
Exactly.
and that is, it is saying that psi n is of order n.
Right.
Like, lower,
Yes, sure.
up to something.
So, Chebyshev second function, that means you just take log of this one.
Yeah.
So, now, one thing that if a prime or key in divides Ln, what was Ln? Ln was the GCD, no, sorry, LCM n. So some prime power divides this, it will mean that pk divides some n for and n in 1, 2, n. In this period, that is, every prime power divisor of this is going to divide some integer in that. Okay? So you may perhaps think of that think that the prime powers add up, but that's not going to be the thing because this is the LCM. So we are choosing the maximum prime power. Okay? The maximum prime power that divides one of these. And that means there should exist some n that this prime power, the highest power of a prime that divides n should divide. In particular, that means that pk is less than equal to n for all prime powers. And how many primes are there which are less than equal to, which are dividing n? So in the prime decomposition of Ln, which primes can appear?
Only the primes less than equal to n.
Perfect. Only the primes less than equal to n. So there can be only pi n primes appearing here. And each of their highest powers will be less than n. Okay. Now, Ln is a product of these primes, these prime powers. So Ln is less than equal to n power pi n, because there are only pi n possibilities for this. Only pi n possibilities. Actually, exactly pi n possibilities, because all of them should. So that implies n power pi n. This is an upper bound for Ln. And then you have n power pi n is larger than 2. What we obtained just is bounded below by 2 power n. So larger than 7. Take log on both sides. That means pi n is larger than equal to n log 2 by log n. Well, that is log n is 2. And for n less than 7, n we have already checked. So this that's the end of this class. Sorry, 12:30. We begin again.